Hi, we're doing section 3.2 today, so we'll be exploring probability a little further. What you're going to notice as we're working on probability in this section, you're not going to be using the calculator as much. Make that a little smaller. We won't need the graphing calculator. For the most part, you can even just use the a scientific calculator if you wanted. So that'll be a little bit easier. Less calculator. And you're also going to find there really isn't as much work to show. And sometimes students like that, but I'm going to encourage you to show more work than you think you need, because it's going to help you think through the problem. Because there isn't as much work to show, it's easy to just do the problem real fast and misinterpret what it's asking for. So I'm going to say less work to show. And then I'm going to say write more than you think. More than you think you need. And as I'm doing the notes, I'm going to probably write more than some of you want to write, but it's also a way of me guiding you so that you can see what's going on in my brain. Like I said, probability sneaks up on you. It's something that maybe initially might seem pretty easy, but as you get going with it, it can be pretty tricky. So the first thing we're going to talk about is what we call the complement of an event. Let me get that going. Oh, it doesn't seem to want to go. So I guess I won't highlight it. The complement of an event is all the outcomes in which the event does not occur. So we typically use A to represent our original event, and some books will use A with a bar over it to represent the complement, or our book uses A with a little, you can think of it like an apostrophe, or we say A prime, that symbol to represent the complement. And complement is spelled with that E. A compliment that you give someone, like, oh, you look nice today, has an I in there. A mathematical compliment has the E in there. So what the complement is basically putting that word not in front of the event. So if we look at the examples here, if our original event was winning, the complement, which we could denote with the A bar or with the A and the prime, would be not winning. And if you're not winning, that means you're losing. And you could probably debate like, well, maybe you tied, but we're just going to say not winning would be the complement for winning. And here, if our event was having a girl baby, then the complement, which again could be A bar or A prime, would be not having a girl. Well, if you don't have a girl, that means you have a boy. So with the complement, right now you may not really feel like how that's going to help you, but as we move forward, there's going to be situations where knowing the complement is going to be helpful. Okay. The next one, we're going to look at disjoint or mutually exclusive events. Sometimes we'll even say disjoint or mutually exclusive sets. And these are events which cannot occur at the same time. They do not have any intersection. And the thing you want to notice here is that complements are mutually exclusive. That means you can't have winning and not winning happen at the same time. And you can't have a girl baby and a boy baby happening at the same time. And I know sometimes people can kind of debate that a little bit, but you have one or the other. You won't have overlap. And one of the ways that I look at this is I'll think of what we call a Venn diagram. I think of two sets. So if we look at this example, it says, are the following mutually exclusive? And the first one we're going to look at says motorcyclists and women. So if we had a set of motorcyclists, I'll just abbreviate that, and we had a set of women, there would be overlap. Right in here, you can have women motorcyclists. So these are not, I'll abbreviate, mutually exclusive. There is intersection. Now, if we were talking about dogs and cats, here's dogs, and here's cats. There's no overlap. You can't have any cats that are dogs or dogs that are cats. So this one would be mutually exclusive. And then if we had dogs and German Shepherds, we could have dogs here. Well, German Shepherds, I'll just abbreviate, would be a subset of that group. So they definitely overlap. So this would not be mutually exclusive. So when we're talking about disjoint events or mutually exclusive events, you have that situation where one set or one group and the other group do not overlap at all. And you can see when you look at this that our complements that we talked about up here, like winning and losing, girl baby, boy baby, are mutually exclusive. They do not overlap. Okay, this next rule we're going to look at is called the rule of complementary events. I just want to get a little space to write here. Your rule of complementary events says if you take the probability of an event plus the probability of its complement, I could also put the probability of A plus the probability of the complement, if I want to use the A bar, equals 1. Okay? That's because the highest any probability can be is 1. So you either will have this happening or this happening. When you add them up, you get all your possibilities. An example, let's say I was talking about heads or tails. Probability that you get tails is 1 out of 2. If you don't get tails, the probability of not tails, that would be the complement, would be heads, is also 1 out of 2. When you add those up, you get 1. So if I know this, I can figure out that. And we're going to do a couple of examples to drive this home a little bit. So this first one, we know that the probability of rain is 0.35. So you can think of this as our initial event. And then it says find the probability that it's not raining. So not rain would be the complement. So you'd either use the A bar or you'd use the A prime. Well, here's what we know. We know the probability of an event plus the probability of its complement equals 1. That's given to us. Well, we know the probability of A right here, the probability that it rains is 0.35. So this would be the probability of rain plus the probability of not rain event and its complement equals 1. And think of it this way. It's either raining or it's not. Those are your options. And sometimes students will say, well, what about if it's sunny? Well, it's not raining then. So we're just talking about it's either raining or it's not raining. Well, if we want to continue with this, the probability of rain is 0.35. The probability of not rain, we don't know, but this equals 1. Now, I know a lot of you can just look at that and see that it's going to be 0.65. We can also use algebra to subtract the 0.35 from each side. And we will have that the probability of the complement, which is the not rain, is 0.65. So you're using the idea that they need to add up to 1. You will get very used to this as we go through with probability, and you'll be able to just do it in your head. You might be able to do it with the next problem. So let's look at this example. It says the probability of getting a cold is 0.9. Probability of getting a cold is 0.9. Find the probability of not getting a cold. Probability of not getting a cold is, well, a lot of you will see it's going to be 0.1, right? Because these have to add up to 1. The probability of getting a cold plus the probability of not getting a cold is 1. This is 0.9. This one we don't know, but we know it needs to equal 1. And again, you could subtract the 0.9 from each side, and you'll get that the probability of not getting a cold is 0.1. So again, writing it out, I'm doing it very formally, but a lot of you will be able to figure it out just in your head. If you get stuck, you notice with a lot of these, I'm going from the words to the symbols. Sometimes students will have a hard time at the beginning getting from the words to the symbols. That's why I'm making a point to write that out. All right. The next part we're going to look at is something called compound events. And we will talk about these more. You think about a compound sentence, say, it's connected with an and or an or. So a compound event has 2 or more trials. Something happens and something else happens and something else happens. Something happens or something else happens. So we're going to be discussing the and ones in this section. So this one says the probability that A happens and B happens. And it's telling you here, A happens first, B happens second. The way we figure this out is we'll take the probability of A and we'll multiply it by the probability of B. So I'm going to write the word multiply. Okay. This part right here, I put little asterisks by it. You want to remember when we do this, some of them will be easier than others. If A happened first, sometimes it impacts what the probability for B is. And we're going to have to discuss that a little bit. So the probability of A and B, A occurs first, you find that probability. B occurs second, you find that probability, and you multiply them together. But you do keep in mind that A happened first, so sometimes it changes what happened in the second event. Okay, now what I'm going to do here, because I want to have some space, I'm going to remind us that the probability of A and B means the probability that A happened multiplied by the probability that B happened. So we're going to remember that. And this example I really like. if we were meeting live, I typically try to make this very visual. So I'll try to draw a little picture, and you're gonna notice my artwork leaves a lot to be desired. I am a very left brain person, so very mathematical, analytical, not so artistic, not so creative. So I'm going to talk about this example of names in a hat. And this example I will often reference because with probability, if you can visualize this situation, you can apply it to other situations. So let's say I have this big hat here, or a bucket, or, you know, some kind of bowl or something. And I put little slips of paper in here with everybody's names that are in our class. Okay. So I've got everybody's names. It kind of makes me think of too, like I know when my kids were in elementary school, they used to have the little popsicle sticks and they have everybody's names in there, and then the teacher would grab one out and that would be the person that they asked the question to, or that would be the person that got to run an errand to the office or something like that. So let's say for our situation, we have all of our names, and let's say, I think we have about 35 people in the class. So there's 35 in there total. Sample size, 35. And I'm gonna draw 2 names. I'm just looking at my paper here. I'm gonna draw 2 names, and those 2 people do not have to do the project, okay? And if we were in class, I'd say, okay, who wants to have their name drawn? And I usually see lots of hands. So I'm gonna say, what's the probability that I draw out Andrew's name, and then I draw out Jenny's name? And we don't have an Andrew and Jenny in our class. Andrew's my son and Jenny's his girlfriend. So we're gonna draw these names out of the hat. So the first one we're gonna do says with replacement. So what that literally means is we're gonna draw a name out and then we're gonna put that name back in there. Doesn't really make a lot of sense in this problem because you can't have the same person twice. But if we were doing replacement, that means you draw the name out and then you put it back in and then you do the second one. So we want to know the probability that we get Andrew's name first and means we're going to multiply. We get Jenny's name second. Okay. So we're assuming there's only one Andrew in there. So we pull his name out, 1 out of 35. And then because it says replacement, we're going to put it back in the bucket. And now we're going to try to find Jenny's name. Hers would be 1 out of 35. Now, obviously, if there were 2 Jennys in the class, or if there's 2 Andrews in the class, those numbers would be different. So 1 out of 35 times 1 out of 35. If you put this in your calculator, it's real easy. 1 divided by 35, you'll see the fraction in your graphing calculator, times 1 divided by 35. And look at this tiny number I get. I get this 8.16, and I get that E negative 4, which means 8.16 times 10 to the negative 4th. I can leave my answer like that, or I can make it, write it in standard form, which means move the decimal 4 places to the left. You can see this is a very small probability. It is less than 0.05, so it would be considered unusual. So it would be unusual to get Andrew's name first and Jenny's name second. Now we're going to look at how this problem would be different without replacement. And what that means is when we do our first draw from that bucket or from that hat, when we do that first draw, we're not going to replace the name. So we want to get Andrew's name first. We're going to multiply, and then we want to get Jenny's name. So it looks like the same problem. The difference is when we draw Andrew's name, we do not replace. So when we draw his name, we get the 1 out of 35. We took his name out, so one of those goes away. Hers is 1 out of 34. So the total changed because when we took this first name out, we did not replace it. We did not put it back. And if you look up here, this part right here said, be sure to consider the previous occurrence of A. So since this happened, it changed this probability. Now we'll take 1 out of 35 times 1 out of 34. You can just hear me hit my calculator here. 8.403 times 10 to the negative fourth. A little bit higher, still pretty tiny. Okay, so it's still pretty unusual. You can think about this situation maybe like a raffle ticket. You buy raffle tickets. What always makes you crack up, a lot of times they'll wait to draw the grand prize. Well, if they don't replace it, if they draw your name first, you're not in there. Also, the first one drawn has the lowest probability, so you should get the grand prize, really, right? So a lot of times when you're working on probability, think about that situation. If all these things are in a big bucket and I reach in and I grab one out, what's the probability? That will help. Okay, this has a lot of writing on it, so I just want to clear a couple of things so that when we look at this, it looks a little neater. Okay, I want to do that just to make it less cluttered up. All right, so the next thing, and you can see there's a lot of terms, but we're going to be connecting them. If we're talking about independent versus dependent events, when you have independent events, the occurrence of one event does not affect the probability of the occurrence of the other, which sounds like a lot of words. This is the replacement situation. If we go back and look up here, right here, I cannot get that highlighter to work. We go back and look at the with replacement situation. 1 out of 35, that's what we got when we pulled Andrew's name. 1 out of 35, it did not change for Jenny's probability of her name being chosen. So what happened in the first event did not impact the probability of the second event. So those are independent events. What happened first did not impact what happened second. Dependent events, the occurrence of one event does affect the probability of the occurrence of the other. So that would be a without replacement situation. That's this situation here. Because we took one name out first, it changed that probability. What happened here affected this. This probability depends on what happened here. Okay, and we're going to practice with those. So the practice, I have a bunch of examples because really I think that's what's going to help you more than anything is practice. And as we're practicing, I'm going to emphasize writing more than maybe you think you need, because writing that is going to help you understand. It's going to help you get there. It's easy to just write down something really fast and inadvertently make a mistake. Okay, so I want you to see something. 1, 2, 3, 4, 5 examples. Lots of examples. You can reference these as you're doing your homework. Typically, when I look at the homework, especially the written homework, but the MyOpenMath also, I make sure that I'm addressing everything that you need when you're doing those problems. Just give myself a little more room here. Okay. When you get a probability question, make sure you understand what it's asking. Make sure, sometimes drawing a picture, just like a word problem, really read it over, really make sure you understand what's going on before you try to solve it. So this one says, if you flip a coin 4 times, what's the probability that you get tails on all 4 tosses? So we're trying to find the probability that we get tails on 4 tosses of a coin. So what that means is the first one's going to be tails. And you know what I like to do is think of the different trials as little blanks I'm going to fill in. So the first one is tails, and the second one's tails, and the third one's tails, and the fourth one's tails. Notice I was emphasizing the and. This would be the probability of tails, and tails, and tails, and tails. And means multiply. So what we want to think about here, we're going to multiply all of those probabilities. Well, what's the probability when you flip a coin that you get tails? You can either use 1/2 or you can use 0.5. Same difference. Most people like to use the 0.5 because they'd rather work with decimals. But if you want to use 1/2, that's fine. We need to think about if these are independent or dependent events. So after I flip this first coin, does it change what's going to happen with this coin? Does this coin say, oh, hey, that was a tail, so I'm going to be ahead? This coin has no memory. So every toss of the coin is going to be independent. So tails here, you could have tails here, you could have tails here, you could have tails here. And you're going to multiply those together. Probability of tails times tails times tails times tails, or what's even easier is 0.5 to the 4th power. 0.0625. Is that unusual? No. So you could get 4 tails in a row, in theory. It's low, but it's not unusually low. Again, compare it to 0.05. It's bigger than 0.05. And again, these are independent. What happened in the first trial did not affect the probability of what happened in the second trial. Did not affect the probability of what happened in the third trial. Did not affect the probability because that coin has no memory. All right, let's look at this next one. Whenever I use this example, I talk about, we have in our hall closet, we have a bunch of flashlights so that if the power goes out, you know, we can go grab one. So we have these 5 flashlights, say, in this closet. And it tells us that the probability that a flashlight doesn't work is 10%. So let's write that down. The probability that it doesn't work, one flashlight, equals 10%. Now, sometimes the fact that it was given to you as a percentage throws people. Remember, 10%, we can write it as a decimal. It would be 0.10, or you can use 0.1 even. So we know the probability that the flashlight doesn't work is 0.10. What's the probability that it does work? A flashlight. I'm going to give you time to think about it. Work doesn't work. These are complements. So they have to add up to 1. So if you take 1 minus the 0.10, you'll get 0.90. And whether you include the 0 or not, it's up to you. You could just use 0.1 and 0.9. I'm including them because sometimes it confuses students if I don't. Okay. This little summary of what we're given at the beginning, they told us the probability that the flashlight doesn't work. We found the probability that it does work. So now we have both of those pieces of information to work with. Now it says find the probability, so we're trying to find the probability that none of the flashlights work. Well, how many of them are there? 5, right? None of the 5 work. None of them work. They're all broken. So the first one doesn't work, and the second one doesn't work, and the third one doesn't work, and the fourth one doesn't work, and the fifth one doesn't work. And again, I think of it as filling in those 5 blanks. What's the probability that this one doesn't work? 0.1. And grab a second flashlight. This one doesn't work. They are independent because this flashlight doesn't know what's going on with the other one, right? Just like the coins. This one doesn't work, and this one doesn't work, and this one doesn't work. You know what? I'm going to do my multiplication that way because I was getting too many dots in there. So this will be 0.1 to the 5th. So this says 1e to the -5. Sometimes this bothers people. There's the decimal. Move it 5 places to the left. So this will be 0.1, 2, 3, 4, 5. So unusual or not? Is this unusual? That is smaller than 0.05, so it's definitely unusual. Okay, so that's good. You know, if you have those 5 flashlights in there, you want one of them to work, right? So the likelihood that they're all broken, that they're all not working, is very low. Now it says, find the probability that all of them work. All of the 5 flashlights work. 1, 2, 3, 4, 5. The first one works. Well, up here, remember, we said the probability that it works is 0.9. And the second one works. And the third one works. And the fourth one works. And the fifth one works. So this would be 0.9 to the 5th. .59049. Make sure I have that right. 59049. Yes. So this, you think about it probability wise, this would be very common. 0.5, 0.6, if you round it, it's in the middle. So it'd be pretty likely to happen. Okay. Now, sometimes when I do these 2 problems in class, students will say, well, what about if it was 2? We're not doing those yet because they're more complicated. Because if we were saying, well, what if 2 of the flashlights work? Well, that means the first one and the second one could work, or the first one and the third one, or the first one and the fourth one, or the first one and the fifth one, or the second one. You have to go through all those combinations, and it's something called a binomial. So those get a little more complex. We're just starting off. So right now you'll see more like all or none. All right. Let's do some more examples. There we go. I couldn't get it to scroll. And you'll notice I like to get a nice clean sheet when I start writing. Makes me think a little more clearly. You may find too, if you need more space to write, go ahead and put it on your own paper. Some of you will write on the homework paper or type on the homework paper, and that's fine. But you can also just put it on your lined paper if you want, or you can print out the sheet and write on it. All right, this one says we have 4 men and 5 women, and they apply for a job. So watch what I'm going to do. I'm going to summarize what I have here. So we have 4 men and 5 women. So we have a total of 9 people. So these 9 people are applying for a job. I think this little piece over here makes a huge difference. Oftentimes they give you the information in a paragraph. So if you can summarize that, it's going to make it easier to reference. Also, sometimes they give you the total, sometimes they don't. And students have the tendency to just want to grab numbers out of the problem. You'll also notice 4 was written out and 5 was a number. Read it carefully, because again, there's the tendency of students to just like skim over it and just grab a couple numbers and throw them in there. So read carefully and maybe paraphrase what you have. So the first one says, 1 candidate is randomly selected. So again, I'm thinking of like this big hat with these 9 people in here, and I'm going to pick 1 out. So just like the names in a hat thing. What's the probability that I choose a man? Well, there's 9 total. 4 of them are men. 4 out of 9. So I get 0.444 repeat. That's more like what we were doing in the prior section. Now we're going to move on to B. If 2 candidates are randomly selected, what's the probability that they are both men? Probability both are men. So probability that I get a man and another man. You could think of man, man. It's got the and in the middle, so it's going to be a multiply. So we're going to look at this. What's the chance when we reach in there and we grab out a candidate that we get a man? Well, the first possibility is 4 out of 9. We took that person out. Does it say we're putting them back in? Does it say replace? Also think about it, would it really make sense to have the same person for the 2 people? It wouldn't. So now we took this guy out and now we only have 8. So when we go to grab a second candidate and we want a man, we'll have 3 out of 8. So this is a dependent situation. We would have 4 out of 9 times 3 out of 8. And we'll get 0.167. And I did round that. Oops. Hang on. 0.167. Would that be unusual? No, not unusual. And I'm just kind of throwing that in here and there to remind you not to forget that, to help you remember it. Okay, now part C. If 2 candidates are randomly selected, so now we're picking 2 people again, back to where we started. What is the probability that the first is a man and the second is a woman? And you notice they gave it to you in order. First man, second woman. Because if they just said you get a man and a woman, you'd have to consider, well, it could be the woman first and then the man, or it could be the man first and then the woman. So it says a man first, so we want to get a probability of a man, and so we're going to multiply the probability of a woman. But it says this happens first. So what's the probability that we get a man? 4 out of 9. And we got a man. We took the man out. So now what's the probability that you get a woman? Well, there are 5 women left out of 8. So 4 out of 9 times 5 out of 8, 0.278. Again, that would be usual. It's greater than 0.05, usual, not unusual. Double negative, but you get the gist. Notice, not a lot of work to show. Some students go directly to here. If you're having a hard time, or actually just as you're getting used to these, I suggest writing a little bit more. Don't try to go straight to the numbers. The writing it out helps you think through the problem. Okay. Let's see what we have next. And again, I'm trying to give you lots of examples because I think the examples will help you the most. Also, it was requested, since you can't stop and ask questions during the video, someone said, can we have more examples? So I'm trying to put more examples in there. If you feel like you have the gist of it, you could play the video a little faster, down on speed. You can also, maybe start reading the video, and then if you do the problems and you're fine, great. If you need more examples, go back and look at some more. Okay, so this one says an office assistant takes orders for sandwiches each day for an office of 11 executives. One day, an assistant is out sick and the sandwiches are not labeled in any way. The executives ordered a total of, and I'm going to write this down, we have 5 turkey sandwiches, 3 ham sandwiches, 2 tuna sandwiches, and 1 veggie sandwich. So altogether, that should give us our total of 11. And I do recommend doing this because you notice it's easy to just look and try to pull the numbers out of here. I think this makes it clear. First question, what is the probability that the vegetarian gets her sandwich? So I think of like a table, and the person that ordered the veggie sandwich walks up to the table and they grab a sandwich. What's the chance they get their sandwich? What's the probability that they grab the veggie sandwich? Well, out of the 11, there's 1 that's a veggie sandwich. And again, if you try to visualize that, I think it will help. 0.091. So again, picture those sandwiches sitting on the table. The person walks up, they grab one. What's the chance they got the veggie sandwich that they wanted? What's the probability that the vegetarian does not get her sandwich? Well, look at all the sandwiches. 1 of them is veggie. How many aren't? Ten out of 11. 0.909. Now, something you might notice here. These are complements. You either get a veggie sandwich or you don't. These are complements. So if I took 1 minus the 0.091, I get the 0.909. Okay? These are complements. So some of you may have thought of doing it that way. Okay, now it says, what is the probability that the 3 executives who ordered ham all get their ham sandwiches? So here's how I think about it. We're looking for all 3 ham. First one's ham, and the second one's ham, and the third one's ham. And means multiply. When I look at this, I think of the first guy. He walks up to the table, or the first person, I guess we don't know if it's a man or a woman, walks up to the table and he wants a ham sandwich. The chance that he gets a ham sandwich is 3 out of 11. So he grabs a sandwich and he leaves. So now there's only 2 ham sandwiches there out of 10. So this guy or person needs a ham sandwich. That would be 2 out of 10. Now there's only 1 left. 1 out of 9. So these are definitely dependent events. What happens here affects what happens here, affects what happens here. And the easiest way to look at that again is by visualizing or almost reenacting it in your head. .006. And as always, I want to see your work. This would be your work. This would be your result. I don't want just this number. I want to see where it came from. Because also, let's say you rounded this and you rounded wrong. I don't know if you did the work right. So be sure to show the work and the result. Okay. The bottom one says, would it be unusual for all the ham eaters to get their ham sandwich? Well, we just found that probability is 0.006. To find out if it's unusual, we compare it to 0.05. It is smaller. Again, this has 1, 2, 3 digits. 6 is smaller than 50. So yes, it would be unusual. Rare. Unlikely to happen. All right, I think we have one last example here. And this example, I don't know that you're going to have one like it in this book. Our other book did examples like this, but I just want to show you kind of how this works. It says you have a family and they have 2 children, which is my family, but you don't know their gender. Now, I think I told you I have 2 boys. First thing it says, list all the possibilities for having 2 children. So here's what I want you to think about. First child, second child. There's 2 possibilities, boy or girl, for the first child, and 2 possibilities, boy or girl, for the second child. So we should have 4 different combinations. So I'm going to say here 4 possibilities. So you could have, and I'll do my situation first, you could have a boy first, and then you can have a boy second. You could have a boy first and then a girl. Or you could have a girl first and then a boy. Or you could have 2 girls. So we have all 4 of our combinations. This question says, find the probability of having 2 girls. Well, we have 1, 2, 3, 4 situations. How many of those have 2 girls? Just 1. Find the probability of having at least 1 girl. I want to talk about this term, at least 1. Probability of at least 1 girl. This terminology bothers some students. I want you to just, don't think math, just common sense it. If I said, I have at least 1 girl, I have at least 1 daughter, that means I have 1 or more. Girls. The other thing you could think about, sometimes I talk about it with grades. If I have at least 1 A, that means I have 1 or more A's. So when we look at this, if you have 1 or more girls, let me get a different color here. If you have 1 or more girls, there's not 1 girl there. There's 1 girl here, there's 1 girl here, and there's 1 or more girls there. So this would be 3 out of 4. It's not that situation. And we'll build on that later. So So we're just trying to kind of start thinking that way. The last one says find the probability of having at most one girl. At most, you have one girl. Well, let's go over here. Let me get these guys off. At most, one girl. The most I have is one girl. Well, there's one girl. There's one girl. At most, one girl. Oh, there's two girls there. One or fewer. One or less. So this one would also be 3 out of 4. So again, I don't know that you're going to have one, but I thought it was a good example and I wanted you to start thinking that way. Okay, let me just look at my notes real fast. I think we're set. Again, as you're doing these, I'm going to go back to the beginning. Look at all that great work we did. Less calculator, less work to show. I'm encouraging you, write more than you think. These, sometimes students think, oh, these are easy. They're harder than you think. And some of you may have a pretty good instinct for it. Some of you may not. So one of the ways to help yourself is to write down some of this stuff. Write down more than you think. It will make a difference. Okay, we're all set. You can finish up with your MyOpen Math and your homework. There is one discussion this week too, so make sure you take a look at that. Have a good rest of your night.